Hi, and welcome back to the fifth project of EE542 Cloud Computing in Fall 2018. This project is for a team project where we create a custom protocol in the application level to transfer files from one node to another. So the objective of this project is to create an IP based. So by IP we mean create packets which can be routed through the present routers and to transfer the file reliably without any loss or without any error, to make sure that we get the right file without data loss on a link of 200 milliseconds delay and a loss of 20%. And another objective is to implement this like a SCP interface, so that we use command line. So the reason why we need to create a new application level protocol is SCP has its own performance limitation. It uses TCP underneath and also encrypts files. This takes a lot of time, a lot of processing time, and then the throughput reduces. So there's a need for a new mechanism so that we write everything on the application level and we flood the channel with multiple packets with a probabilistic model, so that all the packets reach reliably without any loss. For writing scripts, we use Bash. Bash is a born-again shell, which is also an improvement upon the C shell, which has few of the following features with unlimited command history and function names, which we can create like a type def in C, function aliases, and also integer arithmetic, which can be performed inside the shell, which was not there before. Let me go over a few of the commands which we use and also the command line interface for the project. The first one is define data. We use that to create our 1 gigabyte random file which we can transfer from one place to another. We use MD5 sum to make sure that the data of both of the 1 gigabyte file is same. This is in order to reduce the number of character checks. Instead of comparing the files, we use the signature of the file to verify that we have the exact file transfer. Split is a command where we divide the file, 1 gigabyte file, into 100 megabytes of 10 files, which can be transferred by 10 different processes. And cat is of course to concatenate all those files that we transfer into one file at the end of reception. Coming to the command line, /sender is our program. One says the sender ID. We need IDs because we are using 10 different processes, 10 multi-process paradigm, where we need to identify which sender has started, which sender has sent everything, which receiver has received everything. And 2100 says the port number, which can be anything, but we've just set it to 2100. And the next argument is the destination. And the next one would be the file name, which we provide for each process. And the other port is for the port where we listen to TCP feedback. Same thing applies for the receiver. One is the receiver ID, 3100 is where the receiver would listen. Node B is to send back your NACs using TCP, and 2100 is a port number where the sender is listening.
Let's see the algorithm. Imagine that we have a very heavy bag, and this heavy bag is so heavy to lift that we can't take it to our home. So what we do is, what would the perfect solution be is that if you have a lot of people, you can divide the amount or quantity in this bag and segregate it into smaller bags so that people can carry it to your place. So we're using the same concept we have a 1 GB file. This file needs to be sent over a 100 MB link, which has 20% loss and 200 milliseconds of delay. So in order to do this, we're going to divide this 1 GB file into 10 parts, and each part is going to be of 100 MB each. So we're creating 10 processes, and each process is going to be responsible to transfer this 100 MB file. Now let us see what happens at the sender side and the receiver side. The sender can also be interpreted as the client, and the receiver can be known as the server. Using the send setup transfer method, we are going to be sending this file on a UDP based, we're going to use UDP. While UDP is a very unreliable protocol, but we are using this because it sends all the datagrams at once. It does not include any kinds of congestion control mechanisms or flow control mechanisms. The receiver side is going to send acknowledgements back to the sender. The sender is then going to see, or it's going to interpret which acknowledgements or the sequence numbers was not received by the sender in this missing sequence window. This missing sequence window is going to accumulate all the sequence numbers which were not received by the receiver, and then it is going to send these packets again using UDP back to the receiver. So in this way, we have used, this is basically our algorithm, and once all the files are sent, the sender is going to terminate itself, and it's going to be an end of a process. Same goes with the receiver side. This was the algorithm of
the shell file at node A. So over here I'm using clear just to make sure that the screen is clear in first. After that we tried using degree to create a 1 GB file, but there was no end of line, because of which we were facing a few problems. Thus what we did was we used a 100 MB file and we replicated it for 10 times, which creates a 1 GB file. And for splitting the file, we have used the split command on the terminal. After which, over here in the shell file, we are running the sender using this command, where we assign the port number, the sender ID, the name of node B, and then the port number at which it sends back the acknowledgement. Now we need a sender ID because there are 10 different processes running. So in order to make sure that the acknowledgements are coming back from that exact sender, we are using the sender ID. After transferring the file, what we do is we wait for a few seconds to make sure that all the processes have ended, and then we echo that the file has transferred successfully. We also give a timestamp to show that after this amount of time the files were transferred successfully. After creating the files have been created, we use rm to remove the .usc files, and while on node B, which is the receiver, we run the receiver command using this, where it has a receiver ID, port number, the host name of node A, which is the client, and the port number at which it sends back the acknowledgement. And after it, all of them have completed running, all the processes, we do a timestamp and we merge all the files using the cat function and create one file which is data bin using this command. We use md5 sum in order to make sure that both the files are exactly same, and if they are same, then we echo that the files have same content, else the file do not have the same content. After doing this, as there is a 1 GB file and the 10 different files, we use rm to remove it, and then we echo the throughput by dividing the 1 GB over duration, which is the RTT. Now let's go to the data lab and create a NS file. So this was the NS file which was used for this lab, where we are setting the link clause at 1% and 20%, and the link is of 100 MB and there is a 200 millisecond delay. We're giving Ubuntu 16.04 as the OS for both the nodes. Now, after I swap in, I can go to terminal to do the rest. Then we will go to the terminal and SSH into DataLab. We are going to use FileZilla to transfer the C files and shell files from our system to the nodes. In host, we will give users.datalab.net. The port will be 22. As we can see, we are in EE542 folder. We'll go inside the folder of lab 5 and select the files which we want to transfer. Drag and drop. Now we can check from terminal if the files are there. We'll SSH into the nodes. Now we're in node A, over here we'll go in node B. As we can see, all the files are on EE542 lab 5. Now in order to make sure that we don't hog the system, we are going to create a temp directory and transfer everything over there on the nodes. So we'll open temp directory. We'll copy all the files from here to temp directory. For that, this is the command. Now when we open the temp directory, we can see it. As we can see, all the files are over here. We'll do the same for node B. The temp directory is not the shared in node A and node B, so when I open temp directory over here, we won't find the files. So we have to do it individually for both the nodes. We're going to use the cp command to copy. Now as we can see, all the files are on node A and node B.
Go over the code. Let us walk through the environment setup. We are testing this algorithm, we are testing this protocol on two links. One is a link with 10 milliseconds delay and loss rate of 1%, and the second one will be a 200 millisecond with a loss rate of 20%. We also found out that the maximum UDP size is 64 kilobytes. This brings us to how we create packets for our experiment. So each packet has a sequence number, has a boolean which says sent is true or false. We initialize it to false, that means it's not yet sent. And our data is divided into 682 per packet. That gives us about 1,700 packets per process, which when multiplied by 10 gives us 1 full gigabyte of data. Let me now go over the sender and receiver code bases. These are all the header files that we're using. Struct, which is explained a few moments ago. So this would print a line which says sender program started. Setting the timeout for the sockets. This method is to read the file, read each file that is passed for per process, like xa.usc, xb.usc. Every file is read using fgetS, which doesn't open the file as a whole but takes line by line, which actually reduces the memory overhead. And then we add these two respective places. Once this is done, we set up the UDP socket and also the TCP socket for reception. Then we start the transfer. What the transfer does is keep on sending. Let me go over send data. Okay, so what it does is it sends all the 1,700 packets per process, and each packet is actually fired 3 times. That means if I have to send a character A, it's always fired AAA 3 times, so that the chances of one of the packets reaching is pretty high. And once all of the packets are sent, the program then waits for a TCP acknowledgement. Based on that, it would set everything to true, and in case there are any more to be sent, it would go back through the iteration. On the receiver end, we have mentioned the same struct so that we can have proper spokes to take data. After that, prints a receiver program with the index, sets up UDP reception, and sets up TCP for transfer. And so receive UDP packets. So in an infinite loop, it would receive all the packets received from, and then in case there's a error, in case there's a timeout, it would send back using TCP so that the sender can reiterate. Else it would just add to their respective places in our data structure in the receiver end. Once all the packets are received, the did receive all data would return a boolean true, and then we would actually go back and write into a file. So write packets into a file. This would create a new file with x1 or x2 or x3 depending on the receiver ID. So we have 10 files x1 to 10 which are created with .usc extension. After that, it runs 1,700 times, and it also at the end it writes a end of file and then closes the file. Once this is done, it ends the program by closing all the sockets and also writing a log that the receiver execution completed. We can now go over the code base running in Ditter. We've used, as we mentioned before, we've used FileZilla to transfer everything, and now we've used a few commands: copy everything to temp folder and then go into temp folder. Same thing on the receiver, copy everything to temp folder and go into temp folder. Now we run the bash lab a.sh. Let's keep that ready here as well. b.sh. Okay. So this is created the file, and then it's splitting the file into smaller chunks. Once it split the file, it would basically compile our source code and then waiting for the receivers to start. So we can start the receivers, and it basically all the programs are being initialized and the receivers are being initialized here, and each of the receiver is parsing and then printing each of the logs, and then it's sending. So all the servers again prints that server is running and ready to receive connection in their respective ports. So basically now the data transfer is happening. We have removed all the logs because it would basically fill up the whole operation, and then once the transfer is complete, we could not basically go back and scroll back like this. Now, while all these processes are, while all this process is happening, let me go over the next few set of slides. Let's come back to the results later. One future scope is that this current implementation makes use of a multi-process paradigm. What we can probably do is also use pthreads to probably increase more, but we are not sure how much it would increase the throughput by. But our analogy is that one person having 10 hands, and then 10% would have 100 hands, so 100 hands doing work together, which would probably increase the throughput. We've also mentioned the NS file, the two kinds of links that you have tested this on, and yep, we will go through the results in a while. So we are also saving the checksum in a common file so that we can access it. When this script is done, it will basically pull from this common folder so that we can verify whether the checksum was same or not. Right, so once all these packets are sent, we're basically calculating the time, and then we would also check the receiver, which would say reception completed successfully, file written successfully using fputs, and then we are using the cat command to merge all the files and also generate an MD5 checksum, and then running MD5 to check, and then command not found. Okay. Yeah, this would basically say that the MD5 was successfully verified. So the total number of times, so total number of seconds it took was 203. So if we calculate the throughput, we would calculate it as 1024 into 1024 into 1024. That's one megabit. We can megabyte. We are converting this to bits, then divided by 203. This, and then again divided by 1024 into 1024. This gives us 40.3 megabytes per second. Sorry, megabits per second. Going back to the presentation, we see that These are the trial. We've run a few trials before we tried to put the result here. The best case scenario gave us 175 seconds with the packet size being 61682 bytes. Then we used the same formula as we showed before. We got 46.6 Mbps. Thank you. Please let us know if there's any feedback, and like, share, subscribe. Thank you.